All right, here we go. We'll wait about a minute, see if anybody else shows up. All right, here we go. Homework was 12.1. It was on prisms, both total area, fancy word for surface area, and volume. It was those mean looking tables there. Hopefully you did okay on that. Any questions specifically on those tables? All right, here are the answers. Let's see. Number one, I'm going to call these off as the questions would appear. Lateral area is 40. Units squared, and total area is 88 units squared, and the volume is 48 cubic units. Number two, lateral area is 2,400, 2,400, 2,400 square units. Total area is 5,400 square units, and volume is 22,500 cubic units. Number three, the height is 3 units. The lateral area is 54 square units. The total area is 90 square units. Number four, the length is 9 units. The lateral area is 170 square units, and the total area is 314 square units. Number five, the width is 6 units. The total area is 168 square units. The volume is 108 cubic units. Number six, I think we did this one in class. The lateral area was 54 x squared units squared. Total area is 94 x squared square units. And the volume is 60 x cubed units cubed. Yeah, we did do that one in class yesterday. I remember doing that with Matt. Okay, number seven, total area is 54 square units. The volume is 27 cubic units. Number eight, total area is 6e squared square units, and the volume is e cubed cubic units. Number nine, E is 10 units, and total area is 600 square units. Number 10, E is 4 units, and total area is 96 square units. Number 11, E is 5 units. V is 125 cubic units. We did that one in class too, I believe. Maybe that was with the honors class. I forget which one. We either did it in your class or the honors class. Number 12, total area is 24x squared square units, and volume is 8x cubed cubic units. Number 13, 390 units. And the last one, number 14, 8 centimeters. That's it. That was everything. Okay. I'm going to warn you about today's class. Here's the calendar. Notice PSAT now will be not next week, but the week after. You guys are scheduled back to come back on that Tuesday after quarantine, and then we'll do one day, and then we're going to jump right into PSAT. So unfortunately, we couldn't do PSAT prep, and then it culminates in the PSAT test. I don't want to spend any more time reviewing. We've done enough of that. For those of you that are really trying to do well on the PSAT test, you have at least one of the packets. If you go on Teams, I posted both packets. So review day 1 and 2 use the same packet. Review day 3 is the last packet. I know Anna sent me a chat saying, hey, one of these packets is 78 pages long. Do you want me to print it out? I gave you both the language arts portion and the math portion as well too. So if you want to practice both, well, there's your opportunity. If there's any confusion on that, or you're like, well, I can't figure this out, I can send you links to both the practice packets and the answers for those that want to independently do some independent study for PSAT. I do encourage that, especially those of you that want to do the best you can. Absolutely do that. If you need any help on any of the math portion of it, send me a chat or email and send Miss McCullis any chats or emails on the language arts portion. Okay. Tonight for homework is as follows: 1 through 14 on 12.2. It is high school geometry. So instead of doing like, one concept and 6 practice problems, we're going to do one concept and, 1 practice problem. So I think we're only doing a total of 2 practice problems today. It would be very helpful if you don't immediately catch on. It's not that complicated today, but if you don't immediately catch on while you're doing your homework, play this video. I'll have this video posted hopefully by noon, but no later than, say, 3 o'clock. So if you want to wait to do your homework until the video pops up and then play the video of me solving one of the sample problems while you're looking at your homework, that can be helpful as well, too. But as I said, I don't think that today is all that complicated. It's 2 formulas, basically. They're both pretty simple. You've also seen these formulas before in 8th grade. All right, here we go. So the shape today is a pyramid. Well, there's a pyramid right there. How do we know it's a pyramid? Well, let's take a look at it and compare it to a prism. So a prism has 2 parallel sides, and the sides are made up of parallelograms. And if it's regular, then it's made up of rectangles. Well, notice here, the sides are not parallelograms or rectangles. The sides, or the lateral faces, those are triangles. Can you see them? And they're triangles that all come to a point. That's what makes a pyramid. So this is the definition of a pyramid. Well, it's 3-dimensional. It's made up of polygons, so it's a polyhedron. The base of this pyramid will be a polygon, any polygon. Could be a square, could be a triangle, could be a trapezoid, could be an octagon, right? Any of those are fine as long as it can't be a circle, but it can be any polygon. The sides of it, we call those the lateral faces, are triangles, and all of the triangles meet at a single point at the very top. That's what makes a pyramid. So the base is a polygon, the sides are triangles. Those are the key words. If you don't stop me, I'm going to talk probably a bit too fast on these videos. So obviously, if you're watching this live, you got to speak up. Otherwise, I'm going to move on. Obviously, if you're watching on the video, you can hit the pause and what did he say? But if you're watching live and I start talking too fast, please stop me. All right, parts of a pyramid. There's going to be lots of definitions here. Make sure I'll make sure I go slow here. Make sure you write these down. So there's a pyramid. Looks like the bottom in yellow there is not a square, not a rectangle. It's a pentagon. So yeah, you can have a pentagonal pyramid. There's one right there. So the bottom, what we give the name to the pyramid is called the base. That is the polygon that all the sides, the lateral faces, they all share a common edge. In other words, the triangles meet the base along, and they form an edge. You can kind of see that. So AB is an edge, BC is an edge, CD is an edge. So base, that's pretty easy to understand. The second one are the sides. Just like in the prism, we call them lateral faces. And the key thing here to remember here is that they will always, always, always be triangles, lateral faces, the triangular sides of the pyramid. Where the triangles meet at the very top, we call the vertex. That seems like that would make sense. Where the triangles come together, that's the lateral faces. Where they intersect, all of them intersect, is that one point there at the very top called the vertex. The perpendicular distance between the base and the vertex is called we probably would have called it the height in 8th grade. We're going to call it the altitude in higher level math. We're going to call it the altitude. And yes, it will literally be abbreviated H. And you're like, well, why can't they just call it height? The reason is we're going to have more than just regular pyramids here. We're going to have ones that, I'll go ahead and say it, oblique. And we measure the height away from the pyramid. And so therefore, we're not comfortable with calling it the height. We call it the altitude. All right, well, here's another one. Let's see, that one's got the base there. It's got 6 sides, so that's a hexagonal pyramid. Do you see the L? I'll do this one more time. That shape right there, the one that's blinking. Do you see the L? Yeah, that is an L. It's italicized. A lot of books will write cursive L. That is called the slant height. Notice it's not the height. In fact, it's longer than the height. It's called the slant height. Well, you can kind of see it's a little slanted, so that kind of makes sense. Well, it does measure a distance between the base and the vertex, but it's not from the center of the pyramid. It's coming from, well, one of those edges that are formed between the lateral face and the base. You can see the little right angle there next to the, or close to the L. We call that the slant height. Notice that would be the height of the triangle that is also a lateral face. So not only is it the slant height, but it would be height of that individual face of the pyramid. So if you were to consider that face to be a triangle, looks like a triangle here in this picture, then it would be the height of that triangle as well too. Suspiciously, I'm giving you that information. We'll be using it here in a little bit. So this is brand new concept, slant height. You didn't hear this in 8th grade. You got height of a pyramid, but you didn't get slant height. So slant height is that distance along the outside from the bottom of the base to the top, but you got to stay on the face. You can't go up from the center. And like I said, there will be no pyramid where the height and the slant height are the same distances. The slant height will always be longer than the height on a pyramid, or the altitude, I should say more appropriately. Okay. I'll pause for a second. Unless you tell me to stop, I'm going to move on to the next slide. Okay. All right, there are two basic types of pyramids, just like there were two basic types of prisms. The two basic types of prisms were right prisms and oblique prisms. We got basically the same thing here, except we call instead of calling it a right pyramid, we're going to call it a regular pyramid. And there's 4 things that are listed right there, and you need to remember these 4 things. So somewhere in your book of truth, make sure this goes. If you are a regular pyramid, 4 things occur. The first one, and this is by definition, we don't prove this, this is by definition. The first one is that the base, the green portion there, is a regular polygon. That means that all the sides of the green shape, that hexagon right there, are the same, and all the angles are the same. You're like, well, it kind of looks squished in this picture. Remember, that's what has to happen when we draw a 3-dimensional object in 2 dimensions, is we have to kind of force that base there to look slightly different than what it actually is. But trust me when I say all those angles, even though it doesn't look like in the picture, if it's a regular pyramid, all the angles of the base, that green hexagon there, are the same. All the sides of that hexagon are the same. That makes it a regular polygon. The second thing, that all the lateral edges, those are the black portions, the black segments that go from the vertex of the base all the way up to the vertex of the pyramid. I'll draw here in red. Well, maybe I better not make it red, make it blue. So for instance, this black line right here is the same length as this one, is the same length as this dotted one. All of these black lines right here that connect the vertex of the hexagon to the vertex of the pyramid, all of those, I left one off, all of those are exactly the same size. Right? That's what it basically says there. That's the third statement. I'm sorry, second statement. The lateral edges are all congruent. The third thing says is that the triangles that make up the sides, we call those the lateral faces, are all congruent isosceles triangles. They're all congruent. That means they're all the same, and they're all isosceles triangles. Now, once again, the picture doesn't do good justice to this. But you have to understand that if it's irregular, all the triangles are congruent and all the triangles are isosceles triangles. That will be helpful in a little bit. And then the fourth and final thing by definition is that the altitude, right, this H right here, this altitude comes from the center of the base. Comes from the center of the base. And that one's kind of obvious. All right, so I said there were 2 types of pyramids. There's one, regular. The second type, and now remember, we're not talking about names of the pyramid. The names would be, rectangular, triangular, quadrilateral, trapezoidal, hexagonal. Those would be the names of them. But the types are regular, and this one right here. Notice all I basically did was take the vertex and I moved it or pushed it to one side, left or right, front and back. And you get this weird looking pyramid right here. Okay, this one is called an oblique pyramid, just like you had an oblique prism where we moved one of the bases left or right. Same thing with the pyramid, except this time we move the vertex. Notice what that does to our shape. The height or the altitude no longer comes from the middle. The triangles are no longer isosceles and they're no longer congruent. You might have one isosceles triangle. Looks like this first one here on the front is isosceles, but the second one clearly is not isosceles. And then they're clearly not congruent to each other. You could still have a regular polygon as the base, though. All right, once again, unless you stop me, I'm moving on. Okay, we're gonna play a couple games today. The first game is we're gonna calculate the slant height. Remember that was the L. A lot of books have it as a cursive L. Our book used italicized lowercase l. There are two methods to calculate this. This is where it's going to get a little bit tricky, so make sure you're paying attention. By the way, you don't need to memorize both methods. Whichever one is necessary to solve the problem will be the one that you need to use. If it's in your book of truth, no memorization, but it needs to be full understanding or in your book of truth. So here is, well, it tells me it's a regular pyramid. Boy, there's a lot of stuff going on here. Notice in yellow there, they've kind of indicated kind of how to solve this. In yellow there, you can clearly see that you have a right triangle. Well, it's a right triangle because remember the altitude of a pyramid is measured perpendicularly. So that point O right there in the center of that square forms a right angle between the altitude and the distance between O and M. So that's a right triangle right there. Well, you can see L right there. We have a side length of 10. Remember, this is a square on the bottom. We know that since it's regular that the triangles, the lateral faces, are all isosceles. So if that's true, where V comes down to M, it would cut that side BC in half. Therefore, that's where we get in this 5 and 5. Lastly, this last 5 right here, the distance between O and M, this last 5 right here, well, we know that O is in the center, so therefore it would be half of 10. Okay, well, there's our distance. Last and final, we got one bit of information here, this 13. It's kind of hard to see what they're trying to say. They're saying that the length of VC is 13. So that's my basic setup, and we're asked to calculate the slant height, the L right there. So two methods. There's two different triangles that are formed using L. Well, there's one of them there in yellow. Can you see it? Right? That's formed between the altitude and the side or the leg between O and M. Well, there's another triangle that also uses L. In fact, there's two more. And that triangle is here in blue, right? It forms two triangles there, right? Can you see them? So you would have BM, MV, and VB would be one triangle. And then the three sides of the other one would be MC, CV, and VM would be the other triangle. Any one of those three triangles can be used, the two blue ones and the one yellow, can be used to calculate the length of L. And it just means that you just need to pick which one you have the most information. So let's take a look at the yellow triangle. The yellow triangle, we don't know the altitude, we don't know H. We know that OM is 5, and we know that VM, we don't know it, it's L. So that triangle only has one side that we know. Take a look at triangle VMC. VMC, notice one side's 13, one side's 5, one side is L. So that's the triangle. We know two of the sides. It's a right triangle. Therefore, we can use a little bit of, there's the triangle there drawn by itself. We can use a little bit of Pythagorean theorem there to find L. L would be the dotted line there in that triangle. So to find L, L would be VM. So that's the unknown. So that side squared plus 5 squared, I can't talk, equals 13 squared. Hey, this is just Pythagorean theorem. Let's see, 5 squared is 25, 13 squared is 169. Subtract 25 from both sides. Take the square root of both sides. So we just found that the length was 12. The length was 12. So there's version 1 of how to calculate L. So if you know a lateral edge, we did 13, and you know the side of a base, and it's regular, you can do this calculation right here. I said there were two ways. I'm going to show you a different problem. It's going to look very similar to this one. I'm just going to change the numbers around a little bit. Well, let's say that you don't know some of that information, but you know some other information. I'm going to move on to the next one. So notice here, I don't know a lateral edge. I don't know how long VC is. But this time I know that the altitude, can you see the 12 there? Kind of hard to see what they're saying there. Hopefully they give you like arrows or diagrams. So if I were to put an arrow, if I were, this comes from your book. If I were to put a diagram, I would probably put an arrow there showing exactly what 12 was. 12 was the altitude there, okay? So notice now, if we think about the three triangles, well, we don't know the lateral edge this time. So now we know L for triangle VMC. All we know is the MC. We don't know the other side. So we want to use the yellow one this time. So this time I'm going to use that yellow triangle there, which has, let's see, I have one leg that's equal to 12, one leg that's equal to 5. And notice this time L is the hypotenuse. So on the previous one, L was a leg. It was the long leg of the triangle. And this time L is the hypotenuse. And that's what will happen depending upon which of the two versions you use. And remember, how do you pick the two versions? It just really depends on what information they give you on the pyramid itself. Okay, so back to this one. Let's see. 12 squared is 144. 5 squared is 25. 144 and 25 is 169. Okay, so 169 square root of 160. Well, it's basically the same problem as before. Okay, all I did was give you different information. So we got L is equal to 13. All right, cool. So slant height. We just calculated the slant height. Big whoop. What the heck is slant height about anything? Well, you're about to see. Let me delete that marking. Okay, second game here is we're going to calculate the height. So the first game was how to calculate the slant height. Now we're going to calculate the altitude or the height itself. So can you see the H there? Okay, same problem, right? Just slightly different what we're calculating. We're calculating the height here. We won't get those three right triangles. This one, to calculate the height, there's only one right triangle there, and that's the yellow one right there. Now you might say, well, I can move the yellow one to the side, right? There's actually 4 of them there on this particular shape. But yeah, it's the same basic thing. And what do you mean 4? Well, remember, you could also come in this direction, and well, there's another one. But that triangle, since it's regular, would be the same thing as the yellow one. You could also, you could go from here to there, and then that slant height. It's hard to draw, right? But that would be the same triangle as well too. That's the power of if it's regular. Okay, so let's see if we can calculate the height here. Well, this one's a bit more complicated because look what we got. We got a height. On that triangle, there's 3 unknown sides. There's L's unknown, there's H, there's 5, but check it out. We could use that power of, we would actually have to calculate L first for this one. So in order to find H for this particular problem, we have to calculate L as well too. Well, we know how to do that one from the previous problem, right? So if we look at the previous problem, right, we would do that calculation, find that the slant height was 12. Remember the triangle? I'll draw it for you real quick for those of you that aren't paying attention. This triangle right here, VMC, that triangle right here, I'll draw it right here. Let's see, this was your L. I always put cursive. This was 5 and this was 13. If you use that Pythagorean theorem, 13 squared is 169. Subtract 5 squared, 25. You get 144. So L is 12. That's where we're getting that from. Okay, back to the problem at hand, which was to calculate H. So we got a 5 and a 12, and now it's just our friend, the Pythagorean theorem once again. Remember, the side opposite the right angle is your hypotenuse. You can screw that up by putting the wrong numbers in the wrong places, certainly. Well, it seems like we've done this calculation a whole bunch, right? 12 squared, 144, 5 squared, 25. This time we're subtracting 25 from both sides, and we get a very ugly number, very ugly, 119. So don't trouble yourself, just leave it as the square root of 119 and you're done. Now, if it's like the square root of, I don't know, 120, yeah, you have to simplify the square root, but there's no perfect squares in 119. Okay, so we've calculated height, altitude. We've calculated slant height. Remember, slant height is the distance along the side of the pyramid from the bottom to the top, measured perpendicularly. We're now going to use both of those techniques to do a larger problem. If you want to change to a decimal, there you go. All right, so now we're going to move on to what we did yesterday. You remember lateral area? Remember the total area, not the total area, the side area of the shape. So that would be the sides of all four of those triangles. Well, luckily for us, back to when we wrote regular pyramid, one of the things that we wrote for regular pyramid, if you go back, let me go back. We go back to that slide that said regular pyramid. It says right smack here, it says all the lateral faces are congruent and they're all isosceles triangles. So we don't have to calculate all four of them. We just need to calculate one of them and then multiply by 4. All right, so let's do that. All right, let's get back to lateral area. Oops, went too far. Okay, lateral area. Lateral area. To do the lateral area, we got to pick one of these triangles, one of them. Remember, we're doing the main triangle. So how about we do VBC? VBC. So there's VBC, and we've already done this calculation a bunch of times. We already know that the slant height, which is L, ends up being the height of that triangle. We know the base is 10, so this one isn't hard at all. Now, granted, it's not hard because we've already done the hard work of finding H and L. All right, so we need L for this one. Let's see, the base is 10, the height is 12. The formula for area of a triangle is base times height divided by 2. So what, 10 times 12 divided by 2, 120 divided by 2 is 60. Easy. Now, wait a second. That's one of the sides of the pyramid. There's 4 of them. So we need to take that and to multiply by 4. So the lateral area would be 240 square units. Now, notice there's not much math here on this page. That's because we've already done all the work of finding what L was. And that did take, a whole page of work. So don't assume that these will all be nice and easy, friendly problems like this one. Unfortunately, it's going to require a lot of work here. Okay, there is an easier way, and yes, you will be getting a formula from this. Let's think about what we just did. What did we just do? Here's all the math that we just did. Well, let's see. We calculated the area of one of the triangles, and we multiplied by how many there were, 4. Well, that would be the same for lateral area. That would be the same as, where did the 10 come from? The 10 was one of the sides of the base. Can you see that? And remember, the very last thing we did was we multiplied by 4. 4 times 10 is 40. Well, 40 is also, anybody see it? 40 is also the perimeter of the base. So instead, we could multiply by the perimeter of the base. All right, times 12. 12 was the height, so we still need height. And the height is that's the slant height. That's L. And then lastly, we do have to divide by 2. All right, so there's our simplified formula for lateral area. Now be careful, this is only for a regular pyramid. So lateral area for a regular pyramid is PL divided by 2. This is why we don't give it to 8th graders. We save it for for sophomore year high school. So let's write this down. This is actually 12.3. And by the way, what I just did there was a proof. 12.3 just simply says that the lateral area is equal to the perimeter of the base times the slant height divided by 2. Now you might be, slapping yourself on the back saying, hey, look, we got a nice easy formula, PL divided by 2. But remember, P is the perimeter. There's a little bit of calculation going on there. And L is your slant height. Unless they specifically tell you the slant height, you're doing some Pythagorean theorem to figure out what L is. Special right triangle, you might have to use that. If they give you angle, they won't tonight for homework. But if they gave you angle measurements, you could use some trig as well too. I guess the point I'm trying to make is this is not as an easy formula as it looks, unless they give you both the perimeter and the slant height. If they do that, then yeah, it's a simple formula. All right, so in your book of truth, the lateral area of a regular pyramid equals half of the perimeter of the base times the slant height. So PL over 2. PL over 2. All right, great. But there's one problem. The problem is that they're also tonight for homework going to ask you total area. And they're not going to give you a formula for total area. They expect you to somehow, I don't know, pull out your butt, right? Where is the total area? Let's think about it. The previous one we did was lateral area. Well, lateral area would be those four sides right there. So what are we missing for total area? We're missing the base. So I would like you also to put this somewhere in your notes. Lateral area, which is PL over 2. Since it's a pyramid, there's only one base, so it's going to be lateral area plus one base area. Remember, capital B doesn't stand for base. It stands for base area. So your book doesn't give you this formula. If I were doing the book, this would be the next theorem. But they don't. They assume that you guys would be able to figure this one out all by yourself. So tonight they're going to ask you lateral area. They're going to ask you total area. They're also going to ask you volume. Volume will be the next formula we do. And the last formula of the day. So total area is PL over 2 plus 1 base area. Notice this differs from the prism formula, prism formula. I almost said prison. A prism formula because the prism formula was lateral area plus 2 times the base area. All right. Next idea. And it's the last idea of the day. This is not a proof. In fact, without calculus, this can't be proven. So this is also the video I showed you in 8th grade, if you remember it. They're going to take 3 oblique pyramids and put them together. Let's see what it makes. 3 oblique prisms. You put them together, and it makes a cube. 3 oblique. Now, all the oblique prisms have to be pyramids, I meant to say. All 3 oblique pyramids, there I said it correctly, have to be the same size. But when you put them together, it makes 1 cube. Crazy, right? This is not a proof, right? This is just a video. You will prove this if you get to calculus. So this is Theorem 12.4, which basically says, well, let's see. If 3 pyramids make 1 prism, then I should be able to take the prism formula, divide the prism formula by 3 to find 1 pyramid. And that literally is what the formula says. Remember yesterday, for volume of a prism, it was base area times height. Well, therefore, if 3 pyramids make 1 prism, take the prism formula, divide by 3. So the formula for volume of a regular, it's got to be regular pyramid equals base area times height divided by 3. And this is the last formula of the day. We will do one example and one example only. If you run into problems tonight while you're doing your homework, send me a quick chat and see if I can give you some help so that you won't have to wait a whole day to get it solved. All right, so let's do our one example. And yeah, you're in high school geometry, so of course it's not going to be easy. It's going to be hard. All right, so here's our pyramid. Let's see. It looks like a hexagonal. We're told it's regular. All right, that's helpful. We're told it's regular, and we're asked to find the volume. Well, we know the volume formula, because, well, it's not going to be an easy one. So there's the volume formula. Let's see what we got. Well, that 6 applies to, that's not an area, that's not a volume, that's just the side right there on the base. So one side is 6, and it looks like they're indicating that the height of the pyramid, the altitude is 12. So, okay, well, I know one bit. I know that H is 12. So if I can just find the base area, we're good to go. Sounds simple, but, oh man, all they gave me was one side. Now, they did say it was a regular pyramid, and we know that on a regular pyramid, going back to that first, or I don't know if it's first slide, that slide on regular pyramids, we learned that if it's a regular pyramid, the base is also regular. That means it's a regular polygon. That means that all the sides are the same. So if one side of that hexagon is 6, then all sides are 6. If one angle is this, then all the angles are that. So we're going to use that to find the answer to what is the area of the base. By the way, this is last chapter. Last chapter, what is the formula for area of a regular polygon? Hopefully some of you remember. The formula for the regular area, for the area of a regular, remember this one's regular, right, is the apothem times the perimeter divided by 2. Tonight for homework, there'll be regular pyramids. So this is how you do it. Remember, this was even the test question, 2 of them. All right, so we got to find the apothem. We got to find the perimeter. Perimeter is easy, right? So if one side is 6, all sides are 6. So let's see, the perimeter would be 6 times 6, right? It's 36. So we know the perimeter is 36. Where did I get the 60 degrees from? Remember, that first step was you take 360, divide it by 6. That tells you this angle right here is 60. In fact, all the interior angles right here, or all the, where the 60 is, all those 6 angles there are 60 degrees. And why? Because we know it breaks up into congruent triangles. We got to find the apothem. Remember, the apothem goes from the center down to any one of the sides. So that red dotted line right there. We do know it's an isosceles triangle. So therefore, if one of those angles is 60, we just cut it in half. That means each one of those angles is 30 degrees. You kind of see where I'm going here. If all the sides are 6, now therefore we know we have a special right triangle, right? A 30, 60, 90 triangle. So we got to go way back, flip through our book of truth, back to special right triangles. This is also why, remember we were doing PSAT prep, it was one of our formulas, special right triangles. Turns out in higher level math, you use special right triangles frequently. That's also why I was there. So we know it's an isosceles triangle, so that we know that that cuts that side of 6 into 3 and 3. Now look at our special right triangle. Can you see that? I'll circle it here. Can you see that X value right here will be this value right here? So we now know that X is 3. We're trying to find the apothem. The apothem is right here. And it says take the root 3 and multiply it by X. Well, we just saw that X was 3. Therefore, we know that the apothem, in other words, the A is 3 root 3. 3 root 3. You're like, wait a minute, your special right triangle says root 3 times X. I just choose to write it as 3 root 3. You could write it as the square root of 3 times 3 as well, too. I find it more confusing because sometimes the radical bar, the square root symbol right there, you don't know whether it should go over that second 3 or not. So I always write the coefficient first. By the way, that's the letter A. So we got to go back. Let's see, we got to go back to this right here and plug in 3 root 3. This is going to be messy. We got to throw 3 root 3 in for A, little a, lowercase a. So I'm going to throw 3 root 3 in for lowercase a. And let's see, let's do this math. Let's see. I can either do 3 times 36 divided by 2, or 36 divided by 2 is 18. 18 times 3 is 54. Either one of those would have been fine. So I get 54 root 3, and that's capital letter A. And why do we need that? Because that is the area of the hexagon, and that is capital letter B. How's that for weird math? Little a, then capital A, and then capital B, right? Hopefully you followed that logic there. So capital letter B, we just figured out was 54 root 3. Ugh, indeed, right? Throw that in and then just simply do the math. Let's see, 12 divided by 3 is 4. 4 times 54, 4 times 4 is 16, carry 1. 4 times 5 is 20 plus 1, 21. So 216 root 3. My word, did that take forever. That was one problem. They're not all this bad, but some of them are. Okay. I said today we're going to do basically 2 formulas. It really was 3, but I would consider the lateral area formula just a part of the total area formula. So we did the total area formula. Remember, total area for a pyramid, regular pyramid, is PL over 2 plus B. And then we just did the volume formula, BH divided by 3. I said we were only going to do one example of each. We did. And that's all the practice for today. I do want you to, if you're live right now, to open up your books. Look at page 485. Look at page 485. I have one example.